All right, this is Pre-Calculus B, Unit 6, Lesson 1, Plane Curves and Parametric Functions. This is kind of a fun study, and I love what technology allows us to do with these. Here's the idea of a parametric function. Parametric. Okay, the word parameter is the idea of a constant that can take on multiple values. Now, we think of that as a variable, but it's not a variable in the sense that it varies or changes over time. In a given context, in a given problem, the parameter can stay constant. Okay, but we have done problems to this point where motion along a line is affected by time, for example. So we might have motion along a straight line being following the formula x or s, x of t equals say t squared minus 5t plus 3, and we talk about when does it turn around, when does it come back, when does it go forward, and all of those sorts of things. Well, parametric functions, basically in two dimensions, in planar parametric functions in particular, we have an x function and a y function. So x, which depends on time, and y, which depends on time. Now, in your lesson, it used f and g. I actually prefer x and y because we understand intuitively what those mean. Motion along the x-axis, motion left or right, is dependent on time and is a function of time. Motion up and down is also dependent on time. Now let's take a classic example. Okay, we're going to hit a golf ball. Okay, and so this is a golf ball, and we're going to strike the golf ball at an angle, and the golf ball is going to leave the tee at an angle of 35 degrees. Okay, so 35 degrees. Okay. So the angle made with the ground is 35 degrees. And the velocity of the ball, the initial velocity of the ball, is going to be, let's say we strike it pretty hard here. By the way, golf balls can leave the tee at over 300 miles an hour. But let's say it leaves the tee at 150 feet per second. Okay, 150 feet per second, which is pretty fast. Well struck ball. Okay. There are, and then the motion of the ball, there's going to be two dimensions in which forces can act. The ball is traveling horizontally, so it has a horizontal component, and it's traveling vertically. It's going to go up, and then it's going to go down. Okay, so it's traveling along a vertical path as well. It's going to have a vertical component. All right, and so this is the initial velocity in the vertical direction, and this is the initial velocity in the horizontal direction. Okay, using a little trigonometry here. Can't be scared of trigonometry. Okay, we know these right triangles are affected by the sine and cosine ratio. I won't go into extreme detail, but the horizontal velocity, the velocity in the x direction, the initial velocity in the x direction, is 150 cosine 35. And the velocity in the y direction is 150 sine 35. Okay, all right. So we have a golf ball struck, and we know its initial conditions. All right. So now that we know its initial conditions, what rules does the golf ball follow? Well, horizontally, except for wind friction. But we're going to make the assumption that we're not dealing with friction. Friction greatly complicates the situation, and if I actually wanted to create an equation for friction, I would have to include that, because that friction is affected by velocity, and so it would be directly impacted by velocity and requires writing and creating solutions for a differential equation, which is far beyond the scope of this class. But ignoring friction, the velocity is constant. So the value or the position x of t is directly proportional to its time, right? Distance equals rate times time. So the distance traveled is the rate at which it's traveling, 150 cosine 35, times the time, t. If it travels 2 seconds, it'll travel twice as far. If it travels 3 seconds, it'll travel 3 times as far. Okay, there's our x component of our velocity. Our y component is under gravity. You may recall this formula: h equals negative 1/2 g delta t squared plus v naught delta t plus h naught. Okay, g is the acceleration of gravity. V naught is the initial velocity, in this case the vertical component. And h naught is the initial height. Now you may have seen it with different variables or different letters used. Sometimes A is used for acceleration of gravity. Sometimes other letters are used for the initial velocity. I like the subscripts because they have meaning to me. Okay, so by this token here, let's fill in what we know. The acceleration due to gravity in feet per second is 32. Okay, the initial velocity in the vertical direction is 150 sine 35. Because we're just talking about the height under gravity. Okay, and the initial height of the golf ball that's sitting on the ground is 0. Okay, so the velocity, the y component, y position, is given by the formula y, which depends on time. Negative 1/2 times 32 times t squared plus the initial velocity, which is 150 sine 35 times t plus 0 if you like. Okay, there we have it. So we have a y component of our motion and we have an x component of our motion. Now if we combine those two things, we can create what's called a parametric representation of what's going on. The position at any given time is x comma y, x of t, y of t, right? So x of t, x, y, x of t, y of t is 150 cosine 35 t, comma, negative 1/2 32, I will simplify to say negative 16 t squared plus 150 sine 35 t. Okay, and your graphing calculator has the ability to graph parametric functions. So does Desmos, and since Desmos is what I have access to, I'm going to bring up Desmos here. So basically what you do is you include a parentheses with a comma, right? And I can graph, say, 2, 5, and graph a point that way, right? But in this case, I'm going to put in a parametric equation. I'm going to put in 150, and the parentheses are necessary because otherwise it wants to multiply the 50 times t. It wants to do cosine t. Okay, so 150 cosine 50 all times t. Negative 16 t squared plus 150 parentheses 150 sine 35 t t. Okay? All right, and let's have a look at what's going on here. You can see the initial position here, and t is automatically from 0 to 1, right? You can see from in the first second the path that the golf ball is going to take as it travels. So when it's 80 feet out, 80 feet out, it's 60 feet up, right? And when it's 100 feet out, it's going to be about 70 feet up, right? And you can see that it's starting to adopt a curved path. And I can vary the number of seconds. So 3 seconds, we can see more of the path. Okay, 4 seconds. Okay, we can see more of the path. And let's play with it. 5 seconds. 6 seconds, and now at somewhere between 5 and 6, 5.5, 5.4, 5.3, 5, 3.6, 3.7, somewhere around 5.37 seconds it strikes the ground. Now you may recognize the shape that this makes, and in a later video we're going to talk about removing the t parameter, the time parameter. And finding the equation of this parabola. But what I really find fascinating about this is I can assign t a value. So let's say t equals 1, and that takes away the graph. But I can now say, well, let's let t go from 0 to 3.57 seconds. Okay, and I can now animate the flight of the ball. And so, actually, it was 5.5 seconds, wasn't it? 5.57, or 5.57. There we go. Let's try that. There we go. Now it's, yeah, actually, yeah, anyway, I don't have the right time. Okay? But you can see the ball traveling now. Of course, it animates going backwards, but and so this gives me a lot of information. There's a lot of information in this. So as I model the flight of objects through the air, golf balls, rockets, this is the mathematics that was used in the space race and launching rockets and putting things in orbit. They wanted to model what was going on in real life. Of course, as I said, there's friction in the real world, and that requires solving differential equations, so the mathematics kind of becomes much more complicated, but we're dealing with it at a fairly simple level right now, even though it doesn't seem simple. All right, so hopefully you get the idea, and any given time results in a position, right, an x and a y value, and I can see where the ball is at any given time. Okay, and we're going to do some mathematics with this, such as answer questions about the flight of the ball. When does it strike the ground? When does it reach the highest point? What is the highest point, right? And how far out is it at both times, when it reaches the highest point and when it reaches the ground, and so forth and so on. Now, by the way, just to give you a sense of realism here, the ball seems to strike the ground somewhere around 510 feet. Okay, I don't know if you know the game of golf, but a shot of 510 feet would earn you the would earn you a world record. Okay, but I believe 300 feet is a pretty big drive. 400 feet is drive competition territory, and 500 feet is unheard of. And that's because the great big friction monster steps in. The faster you strike the ball, the more friction there is. And the path of the ball is actually not parabolic. It actually drops off. It takes off straight and then dives toward the end because friction takes over and slows the ball down. Anyway, so I've gone on long.